Our speaker today is Mahsa Modiri, and she's currently working on as a postdoctoral research fellow in the Department of Agronomy with Dr. Linda Lee. She received her PhD in agronomy and environmental engineering here at Purdue, and she has a strong desire to become a faculty member. So in the midst of all this chaos, at some point she is going to be looking for a position and moving on. So today she's going to talk a little bit about her work related to PFAS. So Dr. Modiri, please take it away.
Okay, thank you, Dr. Sutherland, for the introduction. And I just have a small correction. I did my PhD in civil and environmental engineering, not in agronomy, but that's fine. Both are at Purdue. So today I will talk about two different topics. And the first one will cover what I did for my PhD. And the second one will be about what I'm doing for my postdoc. And then I will try to give some ideas what I want to do for my career in the future. So with that, I will first start talking about the first research topic. So for my PhD, I looked at the photochemical formation of COS and CS2 in natural waters. But first, let's see why we care about these compounds in the environment and why we looked at their formation. So COS and CS2, or carbonyl sulfide and carbon disulfide, are two small sulfur gases that are formed in the natural waters. But given their high volatility, then they ventilate into the atmosphere, where CS2 can get oxidized by hydroxyl radicals to form COS. Then both sulfur gases can contribute to sulfate aerosols, which are well known to counteract global warming and also impact ozone chemistry. So sulfate aerosols can directly reflect some of the solar radiation or can indirectly increase the reflectivity of clouds. But with this, that they have very important role in the climate change, the global COS models have not been able to accurately predict their flux from oceans to the atmosphere. And there is still large uncertainties which are kind of linked with the lack of knowledge about their formation mechanisms in ocean or natural waters. But let's see what's the role of sunlight and why we call it photochemical formation of COS and CS2. So organic sulfur precursors present in natural waters, they do not absorb sunlight, so they will not go through direct photolysis. However, they can get involved in reactions indirectly where they can react with reactive intermediates that are formed upon the absorbance of sunlight by some other water quality constituents. And it's likely that the formation of COS and CS2 happens through indirect photolysis of organic sulfur precursors. And interestingly, when previous literature measured COS concentration in natural waters, they found elevated or higher concentrations during daytime, which was linked to controlling photolysis. But during daytime, they found a lower concentration, which again claimed that the formation is not happening that much in the night, or actually hydrolysis is outcompeting the photochemical formation of COS during nighttime. So it really focused on the role of sunlight on COS concentration in natural waters. But when we talked about the role of indirect photolysis, one should note that indirect photolysis can be, of course, affected by the amount and kind of reactive intermediates, and also the role and also the type and the amount of organic sulfur precursors. And it should be noted that these two can really vary between freshwater to seawater. And these water quality constituents can include salinity, dissolved organic carbon, and dissolved organic sulfur that can vary between freshwater to seawater. And when previous literature looked at the COS concentration in field, they found almost 10 to 20 times higher of COS concentration in nearshore waters to open ocean water. And when another study spiked synthetic seawater with cysteine as organic sulfur precursor and dissolved organic matter, then COS concentration was really elevated. So with this brief introduction, I had 3 different hypotheses and objectives for my PhD, but today I will talk about only 2 of them. And if you are interested in more details, you can refer to our published work in ASMG and environmental science process and impacts that goes through all the details about this work. So the first hypothesis was COS and CS2 photoproduction is strongly governed by water type and the presence of water quality constituents, and also the chemical structure of organic sulfur compounds. So to test this hypothesis, the main objective was to make organic sulfur precursors to react with reactive intermediates that possibly were present in the presence of different natural waters, mostly DOM, NaCl, and carbonate that will lead to COS and CS2 formation. And also to look at the effect of different organic sulfur precursors, where we looked at thiols, thioethers, and disulfides. Then we had representative compounds of each group. The second hypothesis was that DOM is actually the leading water quality constituent that plays an important role in COS and CS2 formation by forming different reactive intermediates. To test this hypothesis, we made organic sulfurs and we had a thiol and thioether to react with DOM or the reactive intermediates formed by DOM that would lead to COS and CS2 formation. So to perform the experiments for the first hypothesis and the second hypothesis, we had real natural waters and we had different natural DOM isolates. And the informations for those are like in my backup slides. If you are interested or you have any questions, we can refer to it. So to test this hypothesis, both hypotheses, I had this experimental methodology where I had real or synthetic water type and they were irradiated by by a sunlight simulator. And then the samples were taken periodically and were analyzed by different analytical methods, mostly gas chromatography and mass spectrometry. So the first objective was to look at COS and CS2 formation in different natural waters and to see how water quality constituents and sunlight really affected their formation. So we also try to mimic and simulate what happens in the nature, and by simulating diurnal cycling, meaning that we had periods of light, dark, and light. So when we did our controls, meaning that we left natural water in a vial without any headspace in the dark, there was no formation. However, when the sample was irradiated for 12 hours, the formation increased. And when we looked at the diurnal cycling, we had increase during light time, slight decrease during dark time, and followed by another increase. So the decrease during dark time was really attributed to the hydrolysis of COS, where we were able to nicely match our data with the kinetics model by modeling hydrolysis of COS. And this effect of diurnal cycling was even stronger when we spiked the sample with cysteine as organic sulfur precursor. And interestingly, when the sample did not go through any diurnal cycling, we had much higher formation, which is shown by this bold red circle here. And when we looked at the CS2 formation, we had the similar findings, but interestingly, the response for the CS2 during dark time was different. So with these experiments, we were able to find out that sunlight is necessary for formation, and CS2 formation is actually needs light at the initial period to get initiated to trigger the formation, but it continues to form in the dark. Or in the other hand, in other words, it is hydrolysis of COS is dominant in the dark, but CS2 hydrolysis is negligible. So with that, we were able to really confirm the role of sunlight on COS and CS2 formation. And we found that the CS2 formation can continue in the dark, but definitely light is necessary to trigger this formation. And then we looked at the effect of different natural waters to investigate how water quality constituents could affect COS formation. COS formation was investigated for after 4 hours of irradiation for 9 different natural waters that they varied in DOC and other water quality constituents. And interestingly, we found a positive correlation between COS formation and dissolved organic carbon content. However, we found that COS formation is not controlled by either salinity or carbonate, and it was also true for CS2, but for the sake of saving time, I'm not showing data here. And then we looked at the role of dissolved oxygen. So I should mention that all these experiments were conducted in the oxygen-free systems. And the main intention for that was to increase the concentration of reactive intermediates and the organic sulfur precursors as much as possible, because dissolved oxygen can quench some of the reactive intermediates and also can oxidize some organic sulfur precursors. And since we were really interested to investigate the pathways, we wanted to keep concentrations high. However, to evaluate the role of oxygen, we put it back in the system, and what we found was to see that COS and CS2 concentration both decreased dramatically in the presence of dissolved oxygen, which implied that dissolved oxygen is not directly involved in formation mechanisms, or in other words, it is not actually the oxygen source for COS. And then we looked at the role of different organic sulfur precursors, where we used the thiols, thioethers, and disulfides, and we investigated COS formation. And we found that thiols, such as cysteine, is the stronger precursor for COS formation, while for CS2 disulfides, such as cysteine, plays more important role. And then the next objective was to move from natural waters to synthetic waters. But let's have a closer look what really motivated us to move to synthetic waters. So I'll go a little bit back. So we looked at natural waters, right? So we saw that COS and CS2 formation increased in the presence of sunlight. And we also found that the water quality parameters such as DOM type and concentration and probably DOS were playing a role, but salinity and carbonate were not really directly controlling COS and CS2 formation. And given the nice correlation of COS formation with DOC, we were really interested to look at the role of DOM more closely. However, since natural waters are really complex matrices, it was not possible to investigate how DOM type or concentration specifically matters, or what are the specific reactive intermediates. That's why we decided to have more cleaner matrices through synthetic solutions where we had only DOM isolates and the organic sulfur precursor. And with that, we were aiming to see how COS and CS2 formation will be affected by the presence of DOM and organic sulfur precursors such as cysteine or dimethyl sulfide. And I will talk only about cysteine here, but we got slightly similar results with DMS as well. So what we did was we had some controls in the dark, and then we added DOM isolates and we irradiated the samples. And what we found was COS formation definitely was enhanced with DOM isolates. However, CS2 was not formed with synthetic solutions and DOM isolates under any experimental conditions tested. And then we really wanted to see which reactive intermediates could be contributing in COS and CS2 formation. And that's why we decided to look at the role of quenching agents, which is basically to remove reactive intermediates selectively from our system by adding some quenching agents that will react with those reactive intermediates. So we use isopropanol to get rid of hydroxyl radical in the system, and we use phenol, trimethylphenol sorbic acid, and again add dissolved oxygen, which is a likely quenching agent for triplet DOM. So with that, we got very interesting results by seeing that when we added isopropanol to our system, COS formation was not affected, which means that hydroxyl radical was not directly involved in COS formation. However, when we added the quenching agents for triplet DOM, we found slightly different results. And although this result was not very obvious with phenol, and the reason was like phenol is not did not really compete with cysteine to react with triplet DOM. But when we use trimethylphenol, which is a stronger quenching agent, and sorbic acid, we found dramatic decrease in COS formation. And also when we added dissolved oxygen, we had even more decrease in COS formation, which was attributed to the dual role of dissolved oxygen that it can play on simultaneously quenching triplet DOM and also some cysteine or cysteine-based radicals in the system. So with that, we were able to claim that triplet DOM is a contributing reactive intermediate in COS formation. And with this summary of results, I would like to conclude that we were able to find that in natural water, COS was formed in the presence of organic sulfur precursors and the reactive intermediates that were likely formed by dissolved organic matter. And dissolved oxygen was not directly involved in COS or CS2 formation. And when we looked at the effect of organic sulfur precursors, COS was mostly formed from thiols, while disulfides such as cysteine was a stronger precursor for CS2. And then when we moved to synthetic solutions with DOM isolates, we found that while COS formation was enhanced in the presence of DOM in synthetic solutions, CS2 was not formed under any experimental condition. And then we were able to cross our hydroxyl radical as a contributing reactive intermediate in our mechanism pathway, while triplet DOM was found to be a contributing reactive intermediate. So I should add that there are more details about this work and the detailed mechanisms and the pathways for COS and CS2 formation, which is already published. So with that, I will move to second topic. And I should say that for second topic, I really did a complete different topic and the research. And I should say that I'm enjoying to really deviate from my PhD and also somehow engage my PhD knowledge into this topic. So for my postdoc, I did look at the remediation of per and polyfluorinated alkyl substances by some nanocomposites that are nano iron nickel coated on activated carbon. But why PFAS? And let's see what is PFAS. So actually PFAS is our daily life every day. So I don't know if any of you have ever watched The Devil We Know, the documentary that released in 2018, or Dark Waters, that was the movie that released, I believe, later in 2019. So both these movies are about PFAS. While the first one is about the problems that the workers of DuPont, the main company that was producing PFAS over years, and mostly the problems that the pregnant woman faced after working for a while in the company. And Dark Waters is about a lawyer of the company that was fighting against PFAS. And then PFAS is in highlights for DoD right now that they're dealing a lot of PFAS contamination. They're addressing PFAS contamination in a lot of military sites. And it's also in EPA that has a lot of money and budget on it right now. And there is a cleanup action going on, which I believe will be in action in a year or two. So, but let's see what is the potential source of PFAS and where is PFAS. So PFAS is mostly found in aqueous film forming foams because it's a really nice and dangerous fire retardant. It's in land-applied biosolids that are applied as a soil fertilizer. It's in Teflon or anything that would repel both oil and water. It's been found in landfill leachates. I'm not quite sure if there is any study on that in US, but I'm pretty sure there are a bunch of it from China that they have found elevated concentrations of PFAS in landfill leachates, and it's also in carpets. But unfortunately, EPA has announced that these compounds are linked to adverse health effects, and these are carcinogens and bunch of other adverse health effects that have made scientists to look for remediation and cleanup of PFAS in the environment. But why PFAS is everywhere? Why people use PFAS? So let's have a look at PFAS structure and chemistry. So PFAS are large highly fluorinated aliphatic chemicals. There are over 5,000 different PFAS compounds formed, and I believe hundreds have been already found in the environment. They have a hydrophobic tail and a hydrophilic head, which make them hydro and oleophobic compounds. They are potentially active and they're chemically stable. But these unique structure and characteristics have made them suitable compounds for a wide range of military and industrial uses that I mentioned in the previous slide. But unfortunately, these structures have also made them recalcitrant and very persistent in the environment. And that's why we see very frequent occurrence in the groundwater, biosolid, soils, and some other environmental media. But among these different PFAS that I mentioned, almost 5,000 different PFAS, some of them will go degradation and natural microbial remediation in the environment. But unfortunately, when they break down, they will form again another PFAS. And most of the times, PFAAs or perfluoroalkyl acids are the terminal degradation products. And they can either have sulfonates or carboxylate head. And that's why most of remediation techniques so far have focused on PFAAs. And among different PFAAs, we have PFAA and PFAS, which are having 8 carbon chain lengths. And right now they have been, I believe, crossed out of the production because of the EPA regulations. And they're called so-called legacy PFAS. And most of techniques so far have focused on these 2 C8 compounds. But these PFAAs or perfluoroalkyl acids have another problem, which is actually they're pretty mobile, which means that if they are in groundwater and mostly shorter chains, they will not soak to soil or sediments, and they will be very mobile and moving in the groundwater. But let's see what has been done so far on the remediation of PFAS. So most of the techniques that are in use right now, I believe it's through sorption, which is using some adsorbents like activated carbon, different polymers, or like filtration and separation technologies. But the problem is like they will only sequester PFAS and they will not destroy PFAS. And there is a likelihood of re-release from these adsorbents. And then we have a huge mass of waste contaminated with PFAS that we need to deal afterwards. And there are some destructive technologies like electrochemical oxidation, analysis, and UV-generated hydrated electrodes. But the problem is like they're not able to break all PFAS compounds. Like electrochemical oxidation, they can only break like carboxylate, and they're not working well for sulfonates, or not like they're very energy intensive, or they are not amenable for in-situ application. So with that, on the other hand, we have zero valent iron. It's a strong reductant, it's environmental friendly, and it's a low-cost remediation technique. And it has shown to mineralize PFAS, the legacy C8 PFAS, but the problem is like it works only in subcritical water. And then there is a problem for the nanoparticles most of the times, and it's the aggregation. And what if we add some catalysts like nickel to enhance the reactivity, or some adsorbents to minimize aggregation, optimize reactivity, or immobilize or reduce PFAS mobility? So this motivated our group to try to synthesize these nanocomposites. And in our previous work that is already published in Journal of Hazardous Material, we were able to show that PFAS can get mineralized at 95% with a product like inorganic fluorine, accounting for all PFAS transform. So this work really motivated us to look at how these nanocomposites will work for rest of PFAS compound, how PFAS structure can really affect the transformation by these nanocomposites. And then we were like, what if we use this nanocomposite under dynamic flow condition? Would it work? Would it mitigate PFAS? So with this, we had the first approach, and it was doing some batch experiments with these nanocomposites with different PFAS compounds. So what we did is we need to synthesize this particle under oxygen-free conditions. So we did it in an anaerobic chamber. Then we put these particles in reactors, and then along with a solid including PFAS, then we seal it in the chamber. Then we take them out, and they are under controlled temperature, either 40, 50, 60, and we found that no degradation happened at room temperature of 40, but we continued with 50 and 60 degrees C. And we did reactions up to 12 days, but most of the experiments were done 1 day and 5 days. And then after termination of the reaction, we looked at the headspace and the supernatant, and the particles were extracted in 2 different ways for organics and inorganics. And we then used different analytical instruments to look through the products. We used the high-res mass spec to see if there is any unknown organics or any fluorinated organics formed from destruction of PFAS. We used LC-MS to quantify targeted PFAS, and then we used IC to look for any inorganic products. And we also characterized the surface chemistry of the particles, and we were able to look at the size distribution and also their morphology. But we're doing more work on the valence of metals and their reactivity and their rejuvenation by doing more work on the surface chemistry. And with the batch experiments that were conducted at 60 degrees C, we found very interesting results. We found that the PFAAs that we tested got transformed after 5 days. And although the transformation was higher for sulfonates, and then we looked at the fluorine formation, and we found that the defluorination of PFAS happened for all PFAAs, although there was a nice correlation between the fluorine formation and number of perfluoroalkyl carbons, which again showed that the shorter chain PFAAs, that they have lower CF2 groups, are more recalcitrant and they're more persistent to defluorination. And then we did more experiments with different PFAS compounds at both 50 and 60 degrees C. And what we found was most of PFAS compounds got transformed and with these nanocomposites. And in addition to the perfluoroalkyl acids, we also looked at fluorotelomere sulfonates, that they're often precursors for PFAAs. And we also looked at Ginex, that it's the emerging PFAS, and it's claimed to be better, or I mean like safer PFAS, but it's a substitute for PFAA. But unfortunately, what you see from this graph is it is even more recalcitrant. So I have no idea why it's replaced by this. And we see higher or equal transformation of PFAS at 50 and 60 degrees C, but I would take your attention to PFAS transformation, which is the highest bar in the middle, which says PFAAs, and how PFAS transformation was affected by temperature. And the highest transformation, almost 94% transformation of PFAS, happened at 50 degrees C. And then when we looked at the defluorination, we found that we have higher defluorination, up to 100% defluorination for longer chain sulfonates, while defluorination was very low for fluorotelomere sulfonates and Ginex. So we looked over all the organic products, fluorinated products with high-res mass spec, but it's possible that there are some organic products and they're not quantifiable, because most of organic products that were found were accounting for less than 1% of PFAS removed. So there is still needed work to see what are those organic products. And with that, we were thinking if we can really use this technique for in-situ remediation. So basically, groundwater can get contaminated by use of AFFFs by military or industrial uses, by the contamination of PFAS in the leachates that can end up in the groundwater, or the land-applied biosolids. So basically, you will have a plume of contamination with PFAS. And what if we use a permeable reactive barrier? And we use a truck with nanocomposites, and we fill that permeable reactive barrier, and we will increase the temperature of the site. And I should also say that it has been done before. We have successful iron particles used as a permeable reactive barrier, and we have site heated, and it's possible to use some coils to increase the heat. And that's why we did lower temperatures, because it really matters to increase the temperature of site to 50 versus 60. And we don't see any formation at 40, but it's worth trying to see if there will be any transformation between 40 to 50. And once it gets reactive, the particles get reactive, and we have all these reactions occurring, then the contaminated PFAS will get transformed to inorganic fluorine and sulfonate when passing through this barrier. So with that, we designed some experiments and under dynamic flow condition. So what I did, I packed a column inside of an aerobic chamber, and then this was the setup I used to test for PFAS removal under dynamic flow condition. So basically the idea is pumping an influent having PFAS either with like different pumps, but the reason to use different pumps was the flow rate that we were targeting. And then a water bath or a heated tape is used to maintain the temperature of column. And the column was packed in a way that we had two support layers at the end and at the end and beginning of the column. And then we had the reaction bed. And we did different column experiments. We did 4 different column experiments, the preliminary experiments with only C8, but 2 last experiments were with PFAAs. The experiments lasted for almost 2 months. And then we played around with some of the parameters that we thought would optimize the transformation of PFAS, which included the flow rate, the temperature, and the ratio of nanocomposites to sand in the reaction bed. So, and after the experimental period was done, like 2-3 months, and then we sacrificed the column. I should also say that effluent was collected daily or based on the experiment, some period of time. And then when we extracted column, we sacrificed column, what we did, we extracted the material based on the methods that we have for batch reactors. We extracted for inorganics and also organics, and we did similar approach to look for targeted PFAS, inorganics, or untargeted, non-targeted search. And with that, we really found some interesting results. So this is the first column experiments with a mix of PFAAs. It was maintained at 60 degrees C. The flow rate was 0.05 milliliter per minute. It was buffered, and sand to nickel ratio, sand to nanocomposite ratio was 10:1. I have a table for Q reference here, and it shows the number of carbon CF2 groups for different PFAAs tested. Basically, what this graph shows is the mass of the compound that was found in the influent compared to the total mass that was introduced. So basically, the breakthrough of a compound out of a column is the first time for the elution of that compound, or the first time that we quantified this compound in the effluent. And as you see from the graph, the shorter chains were eluted first, which shows that they're pretty mobile and no affinity for sorption. And then the elution of rest of PFAS nicely matched their CF2 groups. And like longer chains, they have a really low retardation factors. And when we did the next experiment, next column experiments, we had a lower flow rate. It was maintained at 50, and sand to nanocomposite ratio was decreased. And it made to not to see any longer chains. And actually, the flow rate was lower, and we collected less number of pore volumes. And we only saw that shorter chains were eluted from column. And then we looked at the extract of the column particles. And when we did this, I really looked at the column, and I separated the layers based on the color to see where it has sand or the reaction bed. And interestingly, as you see, so layer 1 to layer 5 is shown by yellow to green, and green is the layers closer to the exit of the column. And shorter chains were found in the layers closer to the column exit. But for longer chains, they were in layer 1, 2, and some of them in layer 3, which means that they were sorbed to the particles and they never eluted from the column. And it was nicely matching by the previous literature that they looked at the sorption affinity of PFAS versus the carbon number, and they showed that the affinity to sorb to the activated carbon increases by increasing carbon number. And then we looked at the percentage transformation, which means that basically how much PFAS we introduced to the column and how much PFAS we collected either in the effluent or the extract. And we were successful by optimizing the condition. And as you see, the green bars here are column 1, and pink color is column 2. And as you see, there is higher percentage transformation for both perfluorosulfonates and PFCAs, perfluorocarboxylates, in column 2 versus column 1. And so when we looked at the total fluorine content, we were able to actually not close mass balance, but we were able to recover 75 to 80% of fluorine in column 1 and 65 to 70% in column 2. And this implied that, again, we have some unquantifiable organic products that they are fluorinated. And even though we did high-res mass spec on all the organics, extracts, and effluents, it was not accounting for most of it. And so we were able to increase transformation from 29% in mixed column 1 to 53% for mixed column 2. So with that, I would like to conclude that the percentage total transformation of the perfluoroalkyl acids were lower in the column study with lower reaction times, and which was 29% compared to the column experiments with higher reaction time, which was almost 56% removal. And so basically our idea was, if you have a column which is packed with nanocomposites or a real aquifer, like a contaminated groundwater, and you will have an influent that will be contaminated with PFAS, PFAS will pass through the column, but different PFAS will have different sorption affinity to the nanocomposites, which will affect their transformation as well. And then when reaction occurs, we will have inorganic fluorine as a product that will be collected in effluent. And then different PFAS will elute from the column, and it will be mostly shorter chains following their carbon chain lengths. So with that, what I did for my PhD and what I'm doing for my postdoc, so I think I can really propose an adsorptive-assisted photocatalysis technique as a green technique for PFAS remediation. So basically the idea will be, we still have nanocomposites, but instead of nickel that needs higher temperature to get activated, we will have a photocatalysis. And then in the presence of sunlight, it will get activated and it will generate electrons. And the benefit of having adsorbent will be, we will have more PFAS available for reaction by making them to sorb onto the adsorbent. And then by creating reactive holes, and at the end of the day, by creating hydrated electrons, we should be able to remove PFAS. So this is what I'm targeting to do in the future. And I would like to thank my postdoc advisor, Dr. Linda Lee, and my PhD advisor, Dr. Misha Shah, to help me and advise me to do all these projects, and also my colleagues that have helped me with doing these projects. I also like to thank the agencies, DoD, USDA, and for providing funding for research topic 2, which is on remediation of PFAS. And I think I am ready to take any questions.
So that was my applauding. Good job, Mahsa. If someone has questions, then maybe you can take yourself off of mute, or you can post it in the chat. Everybody's digesting right now.
Yeah, there were 2 different topics with a lot of information, so.
I have a question. This is Andy Welton.
Yes, Dr. Welton, please.
So the question I have is, we hear about PFAS a lot in the news.
Mm-hmm.
There's a lot of money you hear about going into like different research programs and
Yes.
doing companies, and the military has bases that have contamination. What do you see happening in terms of the next maybe 5 or 10 years about, the money-making opportunities here? Like where is potentially the most money in fixing the PFAS problem?
So you mean like if we will still have those budgets available, or?
Yeah, like, so there's many students here that are master's students, and they're going out into the workforce, and so, where they'll probably see it, but where will they see the most amount of money? Like, will it be consulting? What would consultants be doing?
Yeah, I think they're really right now, most of agencies that I'm aware of, certified, that we just regularly go to the conferences and the talks that I see, I think they're really right now looking for novel techniques and the ideas. So I am not sure how it will go to the consultants, but right now I think it's really at the base of universities from what I see. So like right now they're looking for really ideas of the young scientists, and they're giving even a small monies of like 10, 50,000 just to see the ideas. So with that, I think the money, you're right, will eventually move from the university base to the consultants. And actually we've been in contact with a few companies that are interested in our nanocomposites. So they want to see how it will work in large scale. So I think, yeah, you're right. Eventually it will move from, when there is more fixed strategies and technologies, they will move forward from university based to the real field sites by consultants.
Okay, thanks.
Other questions? Oh, there's one in the chat maybe. So Aaron had a question. Do you think PFAS should be added to water quality standards in the coming years?
Yes, and actually it's not, I think, very easy to change the regulations. Right now, I think we have only for PFAS and PFOA, but I know that Penn State is trying to also include C6, PFHXS. So I think they will include it, but it is not that easy. I know EPA was under pressure like for years to even include PFAS and PFOA, but I think it will eventually be included.
So maybe I missed it. Are folks working on alternatives? Okay, so that would be another potential.
Yeah, but these alternatives, I believe Dr. Lee now has a project for non-PFAS aqueous film forming foams, but they need to be evaluated, because right now, no, like Genex was a substitute, right? But I have seen most of technologies is not working with Genex, but they work for the ones that have been already crossed out. So I think even for the substitutes, then they will be another phase of evaluating these new compounds as substitute.
So this is like the situation a few years ago, maybe more than a few years ago, when they were using asbestos in brake pads, and then they went to the next least bad alternative, and that turned out to be bad, and then they got rid of that one, and then they went to the next baddest one, and so all the alternatives are probably troubling as well. So.
Exactly. And I think for some cases, like the engines of airplanes or the military missiles, it's not that easy to find something working as good as PFAS, because those go very high temperatures, and I mean, they cannot come up with a compound to replace PFAS in airplane engine in a year, right? So maybe for aqueous film forming foams or retardants, it would be possible, but for some applications, like mostly military, it will not be that easy to replace. And that's why they have a lot of contaminated military sites, and they still use some of them because they don't even have a replacement. So, but yeah, it will take time, I believe.
All right. We need more questions. Should I pick somebody?
There was a question by Aaron.
Yeah, I asked that one.
Oh, okay, sorry.
No, that's all right. You know, I could have forgotten.
But I'll ask another one because I'm interested. So I guess, do you recall what courses would be helpful in understanding how to design treatment systems to remove PFAS from water? I mean, what courses, I know you're here at Purdue for PhD.
Yes,
Courses were helpful.
I think because for removal, I believe knowing the chemistry of the compound is really important. So I think I will tell 3 courses: the physical chemical processes with PhD, and analytical chemistry with Amisha Shah, and then environmental organic chemistry with Dr. Lee. So I believe these 3 courses are really playing a role for what I'm doing right now. But for remediation techniques, I would really suggest contaminant hydrology, because groundwater is one of the main sources for water, right? So for drinking water. And I am a hydrologist. I have hydrology background, but I never had a contaminant hydrology. And now I know it's offering in hydraulics. So I'm trying to audit that course actually. So, but I think like combination of these courses and along with some hydrology courses will be really helpful to come up with ideas for remediation techniques, because most of the time you need to know about the fate and transport before being able to propose something for removal. So I think combination of these courses would be really helpful for environmentalists to think differently about remediation and removal of contaminants.
That's really good. Good insight. So here's another question from Aaron. What led you to work on this project? How did you get involved with it? I think that's the question. And what are your future plans within that field of hydrology?
Okay, I like this question because, so for my bachelor, I did civil engineering. For my master, I did hydraulic hydrology. And I was doing a lot of modeling, artificial intelligence for the quantitative approaches for my master. And then I got to the point that I don't know about the chemistry as an environmentalist. So that's why I started doing my PhD as an environmental chemist mostly. But then I think I was in the ACS talk, and then I realized that this PFAS is really creating problems. So everyone talking about PFAS in the ACS. And I knew, of course, Dr. Lee is working with PFAS, and I wanted to work with her. So that's why I approached to her. And this is how I got involved for PFAS. And the whole year that I was postdoc, honestly, I think it every single day how we can remove these compounds from the environment. Because I think if you watch those movies, mostly The Devil We Know, you will think about it as an environmentalist, how I can help people not to get exposed to these compounds. So really, this was the motivation for me to combine my knowledge in PhD and postdoc and come up with some ideas that they are really plausible and they have potential for really applying in the site and removing these compounds from the environment.
Yeah, that's really good. Thank you.
Mm-hmm.
Time for maybe one last question. Going once, going twice. Professor Lee, are you there?
Oh, is she here?
Yeah, she's there. She's lurking. She's lurking in the background. Yeah, you did a really good job, Mahsa.
Oh, thank you, Dr. Wilson. Thank you.
All right, let's thank Mahsa one last time, Dr. Modiri, and good job. And we will be back again next week with, I think we have a faculty speaker from Purdue next week, right? Does that sound right, Krista?
Yes, that is right.
Okay, very good. All right, thank you all very much, everybody. Stay healthy, stay safe.
Thanks, everybody.
All right, bye-bye now.
Bye.
Bye. Thanks, Mahsa.